we are now going to discuss something important called the Equipartition Theorem. But before we do that, we need to define an idea called degrees of freedom. Now, degrees of freedom gets used in different contexts, especially in terms of certain types of engineering. But all of these ideas are related, but right now we're only thinking about it in terms of this thermodynamics study. So degrees of freedom, the definition is that it's the number of distinct and independent modes of energy storage. So what does this mean? We're counting, right? So we literally want a number. And freedom in this case, just remember, is the modes. And you can think of this as types. What are the types of energy storage? Distinct and independent might be different directions, right? So X, Y, and Z are distinct and independent directions. So that's one way to translate this a little bit. So what might this look like? 1 degree of freedom corresponds to each direction of translation. If you have translation, which just means linear motion, in X, Y, and Z directions, that means you have 3 degrees of freedom. You can, in fact, have systems where your molecules, for instance, can only move in 1 dimension. Imagine them trapped in a really, really skinny straw. So, direction of translation. Each axis of rotation can also correspond to a degree of freedom. And again, we'll have to talk specifically about what can rotate because it can't be a point particle. We don't think about the rotation of a point particle, but for other types of molecular compounds, we can. Finally, and this is important, and we're not going to go too much into detail of this, but you can think about bonds as springs. We've introduced this model before. And so if you imagine our atoms on springs, that they might have a spring going in kind of different directions. Potentially it's only 1 dimension, potentially it's 2 or 3. Each component of spring potential energy is going to be a degree of freedom, and you also have spring kinetic energy. And part of the reason you have to think about this is that translation is really the whole thing moving, say, in a straight line at a constant speed. But once you start adding them to a spring, you actually get 2 for each spring direction, 1 for the kinetic energy, 1 for the potential energy. So different ways of counting degrees of freedom. Now we're going to do some examples with that and apply the Equipartition Theorem. The Equipartition Theorem says that the thermal energy of a system is equally divided among all of the possible degrees of freedom. So that's just like saying that you have, say, 3 drawers in your dresser, and you're going to distribute your socks in them. Instead of putting all of your socks in the top drawer, you're going to divide up your socks and put them in each drawer. That's the idea. So where this is helpful then is we get to specify how much energy is in each degree of freedom based on how many particles there are, where this is molecules or atoms, and what the temperature is. So 1/2 NKBT goes into each degree of freedom. Or this could be little n RT, though we usually use this form. Now this should look familiar because 3/2 NKBT is what we said thermal energy was for our monatomic gas. So 1/2 NKBT is per degree of freedom. Now let's see how that plays out. So our monatomic gas, how many degrees of freedom are there? Well, it can't really rotate. There aren't any springs involved, so all we deal with is translational kinetic energy. And there's no reason why it can't move in 3 dimensions, so it has 3 degrees of freedom, which are simply the translation in 3 different directions. So then the Equipartition Theorem predicts that 1/2 KBT is in each degree of freedom. So what that means is we multiply 1/2 NKBT by 3, and we get this equation, which is exactly what we already had. So we calculated this by thinking about microscopic speeds, but now the Equipartition Theorem is literally a shortcut to get here. So the Equipartition Theorem is kind of coming from nowhere in a way, but we can then use it to think about much more complicated systems where we can't calculate it as easily from first principles as we did this. So you can get to this 3/2 n kBt either from the equipartition theorem or from the detailed calculation that we did. So now let's look at a different type of system. Again, monatomic gas, we already knew this from before. What's something new? We can look at solids. Now remember that our solid model is basically a crystal where we're using a ball on spring model. So every atom is connected by springs to the atoms around it. So we have to think about the kinetic energy that it has bouncing back and forth on the springs and the potential energy that it has stored in the springs. Now, this is actually a little bit different than the translational kinetic energy because in this case, it isn't that the whole solid is flying through the air, but that each of these balls on the springs has both kinetic and potential energy. So when I say translational motion, it would be better here to just call this spring kinetic. That would be a better phrasing of this. So we have 3 directions of spring kinetic energy, right? Because each of these has the ability to boing up and down in y, x, and then z. But then we also have 3 spring directions that are also storing potential energy. So that's a total of 6 degrees of freedom for our solid. And this might actually be a little bit counterintuitive, that monatomic gases, those molecules can fly wherever they want, but a solid, you think of it as being less free. However, it has 6 degrees of freedom. So make sure that you understand what this degrees of freedom actually means. Again, it's ways of storing energy. So even though we would think of these atoms as more confined, they have more degrees of freedom. So what is the thermal energy then? We're going to take 6 and multiply it by 1/2 n kBt, and 6 times 1/2 is 3. So our thermal energy now for a solid is 3 kBt. So this is really important. The temperature of a solid and how that relates to thermal energy is different than how the temperature and thermal energies of a monatomic gas are related. And again, we can think about the heat capacity, that the molar specific heat, and actually for a solid, it would then be 3R, right? So kind of this, the way we did it before, dividing out the N and all of that, you get 3R. So 25 joules per mole K. Again, if you go and look at a table, this is very close. Solids actually have a larger variation in their molar specific heat than monatomic gases did. Monatomic gases were really pretty much all the same. Solids vary a lot more, and one of the reasons for that is that this model is obviously very simplified. So in a solid, for instance, a solid of copper versus a solid of carbon versus a solid of lead or silicon, this model actually does need to change a little bit, and so because of that you see some variations in this molar specific heat. However, this is still really, really close. So again, we know that our model is overly simplified, so we don't see the variations in types of solids, but it gives us the ballpark right value, and we got that through the equipartition theorem. It would have been hard and or impossible to otherwise calculate that, so that's the power of this.